Great. Yes. Very, very important, very complicated. I think everyone said, now needless to say, I may have to ask your name again, but thank you. I mean, really, you're working on a cross-section of the most important problems that we have in front of us. So thanks for joining today and tomorrow, I hope. I don't tire you out too much or put you to sleep too much. So here, okay, so wow. So the title that I chose for this, I kind of like, let me try this anyhow. I like this kind of old school, right? So some theory for hard processes, okay, not all theory. Okay, these little hands drive me crazy when I have them on there. It's interesting. You've had, 3 days of pretty advanced topics, and to some extent, it's not necessarily bad that what I'm going to provide are essentially introductory lectures. So there may be parts, especially right now, this morning, that you're like completely familiar with. But I hope you'll bear with me a little bit as we go through them, because they're presented in such a way as to tie in to the main topic, which is some theory, what I think is in some sense the underlying theory, which makes the kind of activities that we're all involved in, you're involved in just from what you told me, and the kinds of things that I do as well. So in that sense, we're sharing, a lot of the basis, and it's that basis that I'd like you to come away with what I hope is a better sense of. So here's the outline as I have it, and I think my slides represent this. I mean, you will see these are slides. I mean, most of the slides, this is not the first time, but that they've been shown, but some are. In the first part, which we'll talk about and just start talking in a few minutes, is origins and implications of the parton picture. I mean, it's really, this is very elementary and, ideas which undoubtedly you've seen before, but they do lead directly to the technical methods that we use. And so I think it's worth recalling some of these things. So then a little bit about QCD and a little bit about, again, just kind of a review of field theory concepts that we use and that are part of our discussion of QCD hard processes. And I'll introduce here the concept of infrared safety and the central role that energy flow plays in the identification and the calculation of quantities that can be computed and predicted self-consistently in quantum chromodynamics at high energies. Then there'll be a period, probably by tomorrow morning, where we'll really talk about some rather technical things, the so-called pinch surface or Landau equation analysis that enables us to take very simple concepts and apply them to QCD at all orders. I mean, that's in the sense, maybe the central viewpoint that I'd like you to be able to take away from this is that there's some things where we can talk about QCD confidently at all orders in perturbation theory, even knowing that our calculations can be done now at one loop. We really, have automated ways of approaching those. At 2 loops, we're getting more and more sophisticated and capable in what we can do. 3 loops have gone from the horizon to actually almost tangible, but nevertheless, it's just the low loops that we expect to have one way, either analytically or numerically, results that we could compare to experiment directly, but a sense of why this is a self-consistent picture depends upon our knowledge of the structure of the theory at all loops, even knowing, of course, that perturbation theory is not convergent series in 4 dimensions. Anyway, so what we'll spend some time on is wide angle scattering amplitudes. And I know you've heard from Lance, and we're going to hear from him again this afternoon. But this will be less technical, but on the other hand, quite general about where large corrections come in particular infrared poles and things like that in dimensional regularization, in calculations of wide angle scattering amplitudes. And we'll say a little bit about the Regge limit at some point during the lectures. And then finally, the infrared safety for jets, how we can actually prove that to all orders in perturbation theory, the aspects of factorization proofs, at least we'll touch on those, and evolution that I'm sure you're familiar with, and a bit about resummation. So here, I'll read what I wrote just to kind of remind myself. Some of the concepts underlying, it says, in the use of perturbative QCD to study hard interactions at the Large Hadron Collider and other accelerators past and, like the EIC, proposed, and the Muon Collider, while we're proposing things, the FCC. The emphasis is on simple examples and on the nature of all order arguments. And I do recommend this review by Yuri Dochitzer that appeared in this 50 years collected volume of essays that, well, the archive number is given. So, okay, we got through one of something like 130 slides. So let's take a break. But yeah, any question like, oh, what about? Are there any whatabouts? But what about? Yeah. Well, no. So there is okay. Then we have this wonderful concept of asymptotic series, which says that there are in the world lots and lots of quantities which you can calculate to very, very high accuracy, but which can only be, okay, let me put in, yeah, but can only be completed by additional information. Now, that additional information for us, when we're talking about large momentum transfer processes, is what we call power suppressed corrections, or in deep inelastic scattering, higher twist corrections, things like that. It's only the combination of all of those things that's the actual full theory. What's the full theory? The full theory is the one that nature uses. Nature doesn't get from T to T plus delta T by calculating Feynman diagrams. If delta T is short enough, we can get an idea of what nature is doing by calculating Feynman diagrams. But nature just does the whole thing at once. Okay, so we have certain limits where we can make predictions with what we think of as an asymptotic series. In other words, one that's a well-defined series, which nevertheless diverges at large orders, and which represents some underlying function, which usually involves other scales. In other words, the scales, like the scale of the running coupling, lambda QCD, that appears indirectly in perturbation theory through the value of the running coupling at, say, a given momentum transfer, like the mass of the Z, something like that. Okay, but of course, the running coupling is just a dimensionless constant. So the theory, even though it's an expansion in a dimensionless constant, it has a way of telling us what you have. If you're going to pretend I'm dimensionless or I'm conformal, I'm going to remind you that I have other scales and have one very important scale, is lambda QCD. And so when you start calculating something which is sensitive to that scale, like, for example, you would try to do a scattering at very low momentum transfer, then the theory, I'm quoting now, will remind you, because your calculation will become non-self-consistent. It will start to blow up at large orders. Okay, And so that's the way I'm going to remind you. And then that way you can search for the non-perturbative, what we say now, the infrared completion of the theory. Okay, and so then this is the way it really works, because nature does its own thing. We have ways of calculating, typically perturbative ways, over very short times. But the complete all-time extension of that is something that we can aspire to, but will never truly achieve, requires us to deal with the theory at all scales at once. Here we're dealing with the theory at short scales. Is that sort of helpful? Okay, all right. This is exactly, it would be great to the extent that this is like a discussion type thing, that please keep in mind the questions, the what about questions, okay? Because that, you know, yeah, I mean, the slides are just slides. You could look at them, but okay. All righty. So let's get along to these. Okay, so this is the very, very, to some extent, elementary, both in terms of the understanding that it recalls, and also because it's the elements of QCD, and I'm sure everybody's seen it in some sense. So here we're going to go in this first part, prehistory of QCD. There's actually, I was to this conference, 50 years of QCD, and really, I recommend, I should have put it up there, the pre-QCD history of strong interactions that led up to the discovery of asymptotic freedom and so forth was summarized in a beautiful talk by Robert Jaffe of MIT. And I recommend going on you type in 50 years of QCD or QCD 50 UCLA, and you'll get it. And I think his talk was just particularly useful in getting a historical sense of what was going on. So actually, and his talk made me feel good because it made me think that there are certain things that were before even my time. Okay, so we'll recall deep and elastic and quarks as partons. So what's the basic picture that was developed over the years and that was folded into QCD? I mean, QCD, this whole thing we're going to talk about is sometimes referred to as the QCD improved parton model. And there's a lot of truth to that, okay? But in fact, it's like, you know, it's not the improved parton model, it's QCD that we're going to be talking about, which has the parton model as a limit in the way that relativistic dynamics has Newtonian dynamics as a limit, or even quantum mechanics has classical mechanics as a limit. Perhaps not quite that profound, okay. So then structure functions and scaling, a little bit about that. People can say, oh my gosh, you know, stop doing this. We know it by heart. And then parton model extensions, a little bit about fragmentation, jets and drill. Yeah, and fragmentation, unless you work with it, sometimes it's useful to be reminded of what's going on there. Okay, so this is the first part, prehistory. Okay, so real quick, this is kind of like intellectually what happened. So people didn't know all of these resonances back in the early days, but they knew there were a lot of them, and they kept finding them. Where they would do. This is by, I guess this is Largo Enrico Fermi. So Fermi and Fermi's group at the University of Chicago in the 50s kept finding new resonances, strong resonances, which decayed on very, very large, very small timescales. But it wasn't clear what to make of this complicated structure of hadrons as we went through the 1950s. And so the basic ideas were that somehow all of the hadronic matter was composite yet irreducible. And you may have heard of the term now, and almost certainly you've heard of it now because it's come back into a vogue in a slightly different context, which is the bootstrap idea, that somehow there were no elementary particles, that all the hadrons were somehow irreducible, but yet composite. And maybe they were excitations of that developed into string theory via, well, that's a whole other story. So here's the picture that you would have. This the hadron's a kind of blob. You'd have, say, an electron impinging on this blob. It would scatter. Perhaps you would measure the angle at which it scattered, and then it would produce other things that didn't have any really elementary structure. On the other hand, instead of being irreducible, it could be composites of something else, which is indivisible, or elementary particles, and that was associated with the ideas of the quark model, which also predates QCD, of course, by about 10 years, something along those lines. And here, instead of having this kind of internal string-like substance, you have some dots in there that our little electron is going to scatter off of, and we look at the angle at which it scatters. And then in the final state, it may produce these complicated things, but each of them is based upon some quark constituents. So in some sense, these were the competing pictures that people had. And people were trying to say, is there some other picture we could think of? And basically, the idea, in fact, was no. There really wasn't much else that one could think of as an alternative. And so the problem, of course, the people who were thinking about the quark model said, well, could we produce quarks? So we looked at collisions. We tried to find things that had the fractional charges of quarks and things like that, but nothing was found. So that went by the name of confinement. And the question is, how can you have composites that are really confined? I mean, what does it make sense to think about things that way? And this was in the light of quantum electrodynamics, where, of course, the famous anomalous magnetic moment, the fact that one was able to calculate the anomalous magnetic moment of the electron to high accuracy. And now, of course, the muon is the subject of particular interest right now because of new experimental capacity to measure it. And in the end, nature made its choice. And to some extent, there was a concept called current algebra, which we could sort of talk about a little bit. If people are interested. But anyway, the idea was that there were currents, and really, apropos of where we are now on Largo Enrico Fermi, Fermi's theory of weak interactions, the current interactions. So if you had current, when I was a graduate student, okay, there were these currents and all these papers about currents. And so I went to some professor and I said, what are these currents? I heard of particles, but what are they supposed to be? But in fact, the idea was that by looking at, of course, you start with electricity, quantum electrodynamics. So there you have the charge current and things associated with it. And that had an analogous set of currents associated with the weak interactions. And through even the 1970s, it wasn't entirely clear that these were all vector or axial vector currents, but it turned out they were. But so then there was a sense there were currents. Well, how do you get currents? Well, from quantum electrodynamics, we know we get currents by taking an electron field and its conjugate and putting a Dirac matrix in between, and that's the current. So people had the currents, but they didn't, and they knew there were vectors, but, well, they thought there was the possibility of other Dirac structures, like sigma mu nu and so forth. Those didn't pan out in the nature that we know, the standard model. But they knew they had the currents, but they didn't know what they were made of. Still, the fact that they were currents told you the current has one really interesting property. It's a local operator. So then we get into this very abstract kind of quantum field theoretic viewpoint. You have this local operator that tells you there's a field theory underneath. Okay, it's not quantum electrodynamics, but it's something like quantum electrodynamics. So you say, well, if it's something like it, maybe it's a gauge theory, although people were kind of vague about that. But okay, if it's a gauge theory, then we should be able to find out the fields that are giving the currents. Okay, and to some extent, that was the part where people who were doing the bootstrap thought or the early bootstrap thought, oh, you don't need that. In fact, that's not even the way to look at it. Local field theory is out the window. We're not interested in local anymore. We're interested only in the S matrix. Okay, this is kind of interesting because it's like great ideas come and go. They have their moments when they're just what you need, and other moments when they're absolutely beside the point. So this idea of the bootstrap, it goes back actually to where did the S matrix come from? Okay, we're not going to get anywhere, but what the heck? I was, I just had a transatlantic flight yesterday, so I may talk unceasingly. It was actually, well, the idea of the S matrix is attributed to Wheeler. But it was Heisenberg who really, in the middle of, well, history, let's say, came up with the idea that maybe the way to think about, instead of what we normally think of as local quantum field theory, you should have just this quantity that tells you how states in the distant past turn into states in the distant future. And that's the S matrix, okay? And that's the observable thing. Everything which goes on inside that blob, right? We have a blob, right? So what's a scattering process? You have a line coming in, another line coming out, and then like a blob, something out of a cartoon, and then stuff comes out, right? And he came up with the idea that maybe it's wrong-headed to think we can look inside that cloud, okay, where the cartoon characters are battling it out, okay? And then, but it's only what started that we prepare, and what's finished that we observe those are the only things that we really can observe. And it was associated with the fact that it was really hard to get any sense of a theory for nuclear forces. So even though one had ideas like the Yukawa theory and stuff like that. So actually, I came across I'm a little bit with the Galileo Institute. I'm a little bit historically minded, as you can tell today. I came across a conference that was held in 1946. Right after the Second World War, and people were sort of starting to talk, well, okay, let's get to fundamentals again. And the idea of the S matrix was really discussed in strikingly modern terms, that perhaps we should give up our ideas of local interactions, that local interactions are just too hard, and maybe for strongly interacting things like nuclear forces, it's not the way to look at it. And to some extent, it's an appealing idea, and it makes you think, oh man, now we've really got a new paradigm in which to think. But it wasn't the right idea for right then. Okay, now it's coming back in the context of conformal field theories. Many of these can be analyzed from this bootstrap point of view, only in terms of observables, locality. Some theories may not even have a local, as people like to put it, a local Lagrangian description. QCD, however, has one. The whole standard model has one. And that was yet to be discovered at this time. It was about to be discovered. And that's what happens here next in the slides. Okay. So the current algebra, okay, so these constituents, the stars from the other picture, just as I've been rambling on here, the stuff that's sitting inside of the proton or other targets in the neutron. They provide currents. Currents suggest, oh, if I have a current, well, Fermi knew there were currents, right? Something could couple the currents. Well, a current is a vector. What couples to vectors? A vector field. That way you can make a scalar. So there should be other vector fields in addition to the photon. And since the photon was already taken, you have to have a generalization of quantum electrodynamics. There were the Yang-Mills theories, and that gave predictions for new forces. And to some extent, that's what we're still talking about today. So this was J.J. Sakurai's description of Yang-Mills theory, perhaps the most profound idea in theoretical physics since the invention of Dirac theory. So here we go, deep inelastic scattering and quarks as partons. So now with this philosophical aside, any what about questions? I'm going to think about it while I take a sip of water. Okay. So maybe there were quarks, maybe not. You know, it was interesting because the theory at this point, theory of the place where the strong interactions met theory was dominated, intellectual atmosphere was dominated by Feynman and Gell-Mann. And Gell-Mann was the great name associated with the concept of quarks, Feynman with the concept of partons. But because of their complicated interpersonal connections, apparently neither of them wanted to identify their concept with the other guy's concept. But in the end, we were all dragged kicking and screaming. Actually, the rest of us weren't kicking and screaming. The great men were. Okay, so we had this problem. No isolated fractional charges can be seen. That's confinement. And so one could say, could such a particle be detected? And that's what the early experiments were about. So SLAC in 1969 was kind of where it really got started in earnest. So we want to look closer. So the idea that do high energy electrons incident on a proton or a neutron bounce off anything hard? It's kind of simple, but profound question. So what we look for is the electron momentum k scatters to electron momentum k prime. We can look at the scattering angle and see if there are any point-like constituents. If this process, never mind what happens here. There's an arrow with a question mark. I mean, what's going to come out? How often does this happen? Okay, we'll ask that too. But the main thing is when a large momentum transfer occurs, what's the scattering angle? And then if it does occur, we know there are point-like constituents. If we look at the scattering angle, we can learn about those point-like constituents because, first of all, they're point-like. It's a local current with which the electron is communicating with these particles. So the angular distribution will give information on those constituents. And here's something now, I guess everyone has certainly seen this set of reactions here. The electron comes in, and in the standard model, a lepton comes out. It's either an electron or an electron neutrino in this particular case, because of the exchange of a vector boson V, where V could be the photon, it could be a Z naught for a neutral current if an electron comes in and an electron comes out, or if an electron comes in and a neutrino comes out, or a muon comes in, neutrino comes out, we have the V is a W minus for an electron changing to a electron neutrino, because the minus charge then passes from the electron into the hadronic system, or a W plus. Or it says E goes to mu. I mean, in other words, a mu instead of an E. In the standard model, there's no electron changing to a muon. Now, you find one of those, then you go into experiment because you're going to collect your Nobel Prize. Okay, and so the kinematics, this is a W minus. That's the particle in the standard model. This is W squared. That's a quantity, which is the invariant mass squared of the hadronic system after the scattering. So it's our momentum P plus the momentum transfer Q squared. If that's much greater than the proton mass squared, we call it deep inelastic scattering. And the deep just means more than the proton. Of course, actually, the surprise about all this was that you began to see these effects even when Q squared wasn't much bigger than the mass of the proton. That's sometimes was called at the time, oh, there's a word for it, something scaling. It wasn't premature. Well, anyway, it'll come to me. All right, so yeah. So anyway, in terms of, so here's the parton picture, which is here in the picture here. The idea is that the electron exchanges this vector boson. Now, on the other side, there's a current, okay? This is our local current, which is made from fields, which at that time were unknown, of elementary fields within the proton, the constituents of the proton. So this locality we have here in quantum electrodynamics, here's also quantum electrodynamics, because the photon will only be absorbed if some particles inside the proton are charged. So we expect that in the center of mass frame, this parton has fractional momentum x, where x is between 0 and 1. And we can calculate this process here. And then we'd have an elastic scattering, which is p prime goes to xp plus q. We demand that that be on shell, okay? And so this, well, okay, I'm not going to dwell on this, but if you haven't, I'm sure you've all seen this. So if you have an understanding of it and what you recall doesn't correspond to what I said, we can all learn something by correcting me. Okay, let's put it that way. Oh, that's what we're about. That's the question that will come to us, and that sets the stage for quantum chromodynamics. Okay, so that's exactly the question that people ask, which is posed, as I put it on the other slide. Does it even make sense to talk about? Well, no, that's on a later slide, but okay. So here we are, the miniature version of that. So here's our p prime equals xp plus q. And that's exactly the thing. You can write this thing down, right? So you think about what people knew at the time. They had really no idea if there were these particles there, but they knew if there were a particle there. And I should say they, in this case, it was Feynman who really identifiably posed it in this language, so far as I know anyhow, that if there's a charged particle here, you could calculate this elastic scattering. It's E plus part-time of momentum xp with an unknown charge, but non-zero, exchange a photon to become, and if it's a photon, this L is E at K prime, and here the xp becomes xp plus q, or a p prime. And that p prime squared, we assume, would be small compared to q squared. Okay, so that, they said, you know, does this make any sense? Why is it a problem? Because of confinement. Exactly the point there. They say, okay, but set that aside for a minute. Could we calculate this elastic scattering cross-section? And the answer is, yeah, because we took quantum field theory and it was in the book, you know. Even in those days, it was in the book. So, okay, so here's a little bit more about the, again, this is just a review for, I'm sure, everybody here. Q squared, capital Q squared is usually the letter chosen for the momentum transfer. So it's really minus Q squared. These dashes are tech dashes, okay? So this is not minus Q squared. This is just capital Q squared is equal to minus little q squared in, you know, the space components get a -1 in the metric. And yeah, okay. So that's K minus K prime squared is the momentum transfer. And this we could, if we see something happen, we see the electron coming out in a different direction, then we know for sure there was momentum transfer and we can calculate this Q squared. Right? Another thing, once we know Q, we can also calculate this quantity, Q squared over 2p dot Q. And we call that X. That's the famous Bjorkane X. And Bjorkane came upon that quantity not in terms of this kinematics. He came upon it earlier in his analysis of currents, saying, okay, suppose there are these sets of currents. Suppose something produces these currents. Some unknown constituents produces these currents. Then how could I analyze the expectation values of the commutators and time order products of currents? And he said, oh, this quantity X, where if that quantity is of order as between 0 and 1, then he could make certain predictions. Just in that language of matrix elements and current. It was Feynman, as far as at least the level of history that I know, said, oh, that's exactly the same condition that you would have for elastic scattering. So anyhow, that's the momentum transfer. This, not the momentum transfer, the momentum fraction, just again by setting this p prime squared equal to 0. So you just solve this and you say this x is determined by q. Okay, it's amazingly elegant, the concept behind this experiment. You just see the electron, the thing that you know about, and you're using that really as a probe of something about which you knew almost nothing, with a minimum number of assumptions. Okay, so the quantity y, which you often see, this is p dot q over p dot k. This is the fractional energy transfer. Of course, energy isn't a Lorentz invariant. So it's the fractional energy transfer in a certain frame. Okay, all right, I'll ask you. Which frame? You look at it, y is p dot q over p dot k. We'd like to identify this with a fractional energy transfer. So it's p dot q divided by p dot k, where k is the incoming electron energy. So which frame is this the fractional energy transfer? It turns out to be a very convenient frame at that place. The proton rest frame, which also, it turns out, is the frame in which at SLEC people were doing the experiments. These were not colliding beams. They were about to, well, colliding beams were available at that time, but this was where the target was at rest and the electrons coming in very fast. So the fractional energy transfer in the rest frame of the proton, but anyway, it's a Lorentz invariant, and you can define it this way. And if you define it this way, you get this nice feature, x times y, the momentum fraction times the fractional energy transfer is q squared over s. Okay, both x and y have to be between 0 and 1. X because, well, it's hard to imagine what negative x or x greater than 1 would mean in this context if the proton's in isolation. Actually, x greater than 1 is not so unusual if you're talking about nuclear physics. There, you can have scatterings in which it appears that a single parton has more momentum than a proton would have. Okay, but that's a special case. So the invariant mass squared of the hadronic system after the scattering is q squared 1 minus x over x. And the limit, x goes to 1, where w squared gets small, I mean like 0. That's the limit of elastic scattering. So that's really kind of interesting also in the history of QCD, perturbative QCD. And now at Jefferson Lab and in the future at the EIC, people will really be interested in this limit of elastic or quasi-elastic scattering. Okay, and that's the kinematics. So what actually happened? Well, in the sense, I wrote down here lightning strikes, and that's sort of after being at the talks where people, actually recalled what it was like when this happened. I was sort of like just starting graduate school. I didn't know anything, I didn't even, but anyway, it came out scaling in inclusive deep inelastic scattering. So in inclusive EP inelastic scattering, okay, that's what we've been talking about. The electron, and the amazing thing was it sees these stars, the constituents, which we know are the quarks, as spin 1/2 point-like particles, okay? So point particles, they're ready to give local currents, which is just perfect to the second non-bootstrap way of looking at the strong interactions. So what happens then is that the electron comes in, it couples to one of these by a local current listed as J, and then in the final state, we have a certain momentum transfer or angle in the center of mass frame, which would be the same. And then everything else, it's very, very complicated because you have here a hadronic state whose invariant mass is much larger typically than that of the proton. Very, very few of these have just a single proton elastic scattering. But everything that goes on in here doesn't matter much. The cross-section is essentially given by the scattering of an electron on a point-like particle at some elastic scattering at some fixed scattering amplitude. And so from the informational point of view, the strong force seems like a weak force precisely because there's no sign of confinement. It seems as though, from the kinematic point of view, the parton was just scattered elastically, okay, as if it were a free particle. So people were talking about, actually, it's amazing. You look back at some of these old things, they said, oh, we don't really know what's going on, but suppose it were like free field theory. People were using free field theory as though it were something exotic, but yet it was exactly the right analogy to make. Then you found out that that was the limit, a limit of a theory, which is the theory that actually applies in nature. So the strong force seems weak, almost irrelevant to the electron. The quark parton model, okay, which was the first step in development of QCD, we ignore all interactions between the elementary, strongly interacting constituents. And we have, here's our formula then. So this is the beginning of perturbative QCD as the parton model. D sigma EP inclusive. Now, as we'll see, inclusive is like really important. And using the words inclusive and the concept of inclusivity on final states. This is a quantum mechanical measurement problem, okay? And it's a concept that will get us a lot as we move along. So d sigma EP inclusive as a function of the momentum transfer is like E on star, okay, meaning a quark, goes to E on star elastic scattering at lowest order in quantum electrodynamics times a quantity which is the probability, it should be of a parton with momentum fraction x times p, okay? So, I mean, there has to be some x, parton with momentum fraction x to be there to get that elastic scattering, and that's the quantity which just multiplies the lowest order. But the point is here, this angular dependence is all in this lowest order electroweak process that you can calculate. And to some extent, the whole, I said, oh, well, QCD isn't just the improved parton model, but to some extent, a lot of it is in there in the parton model. Here, we generalize this. We generalize this formula in a number of ways, basically by showing, generalizing this from quantum electrodynamics to QCD. And that's basically, we had to wait until the 1980s to really see QCD reactions in a form that generalizes this. But that was done at CERN, at the SPS, and we'll see some of the plots of those as we go along. Okay, so now everybody's seen this before, and I'm kind of hoping that this review is not intolerable. Yeah, what are there any whatabouts? No whatabouts? Okay, what about the next slide then? Okay, so here, let me drone on with this. I'm fond of this. Actually, I did this slide a long time ago, but I still use it. Okay, so this is the parton interpretation. It's really Feynman, 1969. There's a paper in 72, I guess is the book that he wrote about these things. You think about this process in the electron's rest frame. You can see, okay, question to the class. What figure represents the electron? Well, in case you didn't get it. Okay, so there's the electron, enjoying life as electrons do. And here we have the proton, okay? And here you see a number of these confined quarks. And you can tell they're confined because they're sort of getting tired of each other. Why are they getting tired of each other? They've been there since Big Bang nucleosynthesis, okay? I mean, they had a lot of adventures, they had gravitational collapse and they had a supernova. Maybe they went through that several times, but all that stuff, they stayed together. And they, you know, so this is the electron's rest frame. So there, the proton is like going fast, you know, from our point of view, sitting some, you know, it took a block of carbon and stepped away. Okay, turn the electrons on. But, you know, in the electron's rest frame, it's like moving. And so since it's moving fast, it has a well-defined longitudinal momentum and the fractional momentum of each of these sour-looking guys. So from the point of view of the electron, the proton has certain properties. It's flat because of our friend Einstein. Okay, so Lorentz contracted. Well, our friend Lorentz, Lorentz contracted. It's frozen because of, oh, say the words. What do we say about things that are moving really fast, you know, past us? We say, what about a concept? Then, okay, first word is time. What's the second word that goes with time in this context? Right. I was about to say begins with D. So time dilation tells us that, yeah, why are they together? Because they're exchanging stuff. And people, the word gluon, by the way, definitely predates QCD. They said, oh, if there's a field theory picture of the strong interactions, there's some particles exchanged. Maybe it was a scalar, maybe it was a vector, but it was a gluon. There were scalar gluons, vector gluons. There were vector gluons in U1 models of the strong interactions. But people didn't know at that point how to renormalize the Yang-Mills theories. So they were a little leery about trying to use that. So they're frozen. Okay, so in other words, during the time in which a proton, so if the proton missed the electron and went zipping by, and the electron tried to see what was going on by exchanging very soft photons with it, it would say, oh, they're moving really slowly, right? It's the scale of exchanges of, say, gluons, whatever they were in this, as people thought about them then, would take place in the rest frame. It would take a certain amount of time, 1 over lambda QCD in our language of today. But if you boost that to a frame in which the proton is approaching the speed of light, that 1 over lambda QCD becomes gamma over lambda QCD, right? So it's a much, much longer time. So there's almost no momentum transfer between our partons as they approach the electron. And from the electron's point of view, it's unexpected. Unexpected in what sense? In the sense that there's no way for the proton to send a signal to the electron to get out of the way. Or if the electron, likes to do this, oh, come on, I mean, well, there are charged particles inside the proton. So generally speaking, they would attract the electron. Okay, I mean, the Coulomb force would say to electrons in the neighborhood, hey, big plus charge is coming at the speed of light. Let's have some fun. But no, because the signal wouldn't have time to get there and come back as the proton approaches the speed of light. It would only happen when the proton's like really close. Okay, I have a slide about that too. Okay, so there it is, flat, frozen, and unexpected. It comes to the electron at rest. And afterwards, the electron is scattered. Here, the stars are little soft photons. And the particular guy, here's XIP. This is the parton that's fated to hit this electron. XIP is liberated from the proton, at least in the parton picture. And then the rest of the partons, the fragments, or so-called spectators, just go forward. And so they're still a little unhappy. This guy's happy because he got out, at least temporarily. And this is what the picture is of deep inelastic scattering. But this idea of flat, frozen, and unexpected is not unique to quantum electrodynamics, a process that we base deep inelastic scattering on, but it also applies once you have the idea that the strong interactions are a local quantum field theory, they also apply to QCD. So therefore, these can be thought of as potentially a picture that we could apply to two protons colliding. And that's, of course, what we do at the LHC. Okay, so here, gosh, it's 10 o'clock already. Well, all right, and this is like almost 10% of the slides. So the basic parton model relation, and this is what gives us a concept that we apply in many of the calculations that we've described this morning to factorization. So it says sigma of E on H, where H is a real live hadron, the kind that you and I are made up of. So we can identify, well, at some level, is the sum over partons A of the elastic scattering calculated according to, first semester quantum field theory, where no loops, okay? So at this level in parton model, it's a tree level elastic scattering of the electron on a parton A. And here it's integrated over psi. Psi is a fractional momentum times P, which is the momentum of our hadron, with momentum transfer Q, times the function phi, which is this thing that we call the probability of parton being found with fractional momentum X of the hadron. Okay, except here it's fractional momentum psi, so we're allowing this go from 0 to 1. In the parton model, this phi will be a delta function, and it'll be C minus what? In the parton model, what would C be in the parton model? Just want you to. This is, go right ahead. It's a letter we all love since we started being introduced to algebra. All right, A, B, C, D, E, F, G. Yeah, right. So what? Okay, it's like, this. Is there like a vampire around or something? X, it'd be the Bjorkane X in the parton model. Okay, so X being Q squared over 2P dot Q. All right. Okay, so where sigma EH is the inclusive, so on the left is the inclusive cross section. Now, this is also a pattern very typical of quantum field theory. The left-hand side is something you measure, okay? And then on the right-hand side, there are two things. One of them is something you can calculate. Which one can you calculate? This one, the elastic scattering, because you took the first semester of quantum field theory, right? And therefore, from the epistemological point of view, this is absolutely it. On the right, you have something you can calculate with something you don't know, and you'd like to know more about. It's a structure of some hidden piece of nature. How does a proton share its momentum with partons? So that you'd like to find out about. And you find out by this relation because you can measure the left-hand side, calculate part of the right-hand side, and then you conclude what the unknown object is. This is absolutely the pattern of not just perturbative quantum field theory, but in fact, once you get into renormalization, stuff like that, it's like, it's quantum field theory, okay? And to some extent, it's almost all of science. You measure something, you have some model where you can calculate something, and then you learn about the structure of an otherwise unseen object. Okay, so it's like super profound. So sigma, this is the inclusive cross-section on the left. On the right, the calculable part is the elastic scattering, and okay, here it is for the millionth time. Phi of A and H is the distribution of parton A and hadron H, the probability and the probability distribution for a parton of type A to have momentum XP. So in other words, and the probability would be the integral of phi from a lower limit to an upper limit. That would be a probability. But probability distribution is also dimensionless, so whatever. Okay, it has a meaning. This is the point. This phi has a meaning which is independent of the details of the hard scattering. This could be a neutral current where a photon, or now we would say a Z was exchanged. Or it could be a charge current, where the calculable part, the tree level part, is an electron changing to an electron neutrino, or a muon changing to a muon neutrino. But the phi would be the same. And perturbative QCD, one of the things that we'll try to argue for as we go along in these lectures is the so-called factorization formula, which tells us that at the LHC, we can use these same phis that we saw in deep inelastic scattering to, calculate, to make predictions on processes at the LHC. So there, what will happen is when we make predictions based on a formula like this, okay, well, here's how we do it here. Suppose we said, okay, I know about, I do like great experiments. So I know about the electron, the parton distributions for all the quarks. And so then, because I just did great experiments, a whole bunch of them. And so then I know all the phis for the charged partons. And then I wanted to do scattering with neutrinos. We have a beam of neutrinos. Well, there I can still calculate the elastic scattering just using Fermi theory or the standard model with W exchange. And now somebody told me I knew the phis because they did the experiments. So then I have the prediction for the left-hand side. So in this variation, we know the whole right-hand side. We have a prediction for the left-hand side. And what do? We go to the government and we ask for a couple of $1 billion and euros, as the case may be, and we make the measurement. And then we pat ourselves on the back, okay, because we found it. We found the Higgs or whatever, okay? So this, again, is how we use these. Okay, in words, again, the hadronic inelastic cross-section is the sum of convolutions of partonic elastic cross-sections with the hadron's parton distributions. Now, in some sense, say, why is this the way it is? Okay, so the assumption in technical terms is a quantum mechanical incoherence of the large momentum transfer, scattering, and the partonic distributions. In this case, we can multiply probabilities without adding amplitudes. And you have to try to understand, especially as, QCD practitioners, what we're doing is extremely, I guess the word for it would be heterodox. Okay, it's hetero meaning you change and dox referring to the words. So it's not what quantum mechanics is supposed to be. Quantum mechanics is you calculate the amplitudes to reach a certain final state, and you square the amplitudes, okay? And that gives you the probability. Here, we're saying we calculate the amplitudes to produce a certain parton. We square that, call that the parton distribution, and multiply it times a cross-section, which itself is a probability distribution. We're multiplying probabilities. And people immediately jumped on that when the parton model picture was prescribed, and say, well, why does this work at all? And it comes back, of course, to this question about confinement. So people were thinking, so what did they think about at that time? They said, okay, well, we'll have this anyway. Well, on the next slide, I think. But everybody sort of represents this, or I hope. Okay, and what was the picture of the amplitude? There's Q, and here's XP plus Q. Okay, so people said, okay, so we want to square this. And so they said, oh, well, this is what we're doing here is we're taking this and we're squaring that at fixed X, and we're multiplying it by this squared. Okay, except, I mean, this is on the left in the other formula, this is on the right. And people said, this doesn't make any sense. And so somebody said, well, why doesn't it make sense? Well, he said, in quantum mechanics, what about that? Okay, what about, or quantum field theory, okay? So these spectators are interacting here with our scattered parton. In fact, we expect them to interact very strongly with the scattered parton, eventually producing a system of confined hadrons. This surely happens. So how can you possibly ignore this? And the reason, as we'll emphasize a number of times, is this property of looking at inclusive cross-sections. It's not individual processes. Say this eventually becomes a pion, so maybe this was just proton goes to proton plus pion. And you could imagine how that would happen. Maybe we have a gluon here and another gluon there, and you know, we have an anti-quark here and a quark there, and we lost a quark. Here we get our quark back, and maybe this is the proton again, plus other things, okay? So yeah, this happens. And in fact, this surely happens. And any theory we have has to describe this as being the predominant thing. So in the exclusive final state, this surely happens. But this is the key to the whole thing. It's the fact that we're looking at inclusive processes, that we have this where this is a pion, but also this could have been a kaon. Also, this could have been several pions where a number of pairs were produced and so forth. When you sum over all of these for reasons that hopefully become clear, we reduce to this factorized form. Okay, so it's the concept of inclusivity that's the one that really matters here. So yeah, later we'll see how this works in QCD. Well, maybe if we get anywhere. Okay, so here's the familiar picture. Okay, these are all the things that I said. And anybody who looks at these, I'm sure all of you in the audience know these are parton distributions. They're not the most modern ones, you know. Is anybody here working on? No, nobody was actually part of. Oh, you were. Oh, yes. Oh, okay. But you're a lecturer, so you don't count. Yeah, these you'll recognize as old. She's, you know, what she's looking, she looks at this line here and says, "Oh, how could you say that?" You know, that should be. You know. But and of course, all these things nowadays, everything's in color, and you have these blossoming uncertainties as you go to the limits left and right. But it's still the same idea. Okay, you'll indulge me by allowing me to say it's the same idea. So anyhow, here let's. All right. Well, what the hey? We'll talk about. We'll get to something else later. Okay. So here we are. Here's our friend. This is yet another picture. It's an electron going to the electron, exchanging a photon. This is a proton. And here's our hadronic final state. So here it is in terms of, you know, more technical stuff. The amplitude is a function of the momentum transfer, and also, let's say, the spins in the initial state, and say the spin of the proton and the spins of the incoming and outgoing electron. So here's the QED part that we know. We're saying that this is the Dirac function for the electron. Here's our Dirac matrix with the minus IE, which we got from our, you know, Peskin and Schroeder, our other favorite book. And here we have U bar lambda prime of K prime for our outgoing electron. Here's our exchange photon in the Feynman gauge, just to show that, you know, we remember that there are things like that. And here is the thing which people were assuming. This takes us back again. Before the experiment was done, people could write down this to say, okay, we'll have for a specific final state X, there's a quantum mechanical matrix element with an incoming proton of momentum P and spin sigma, and an outgoing hadronic final state X with mx squared much larger than that of the proton, with some local electromagnetic current. How do we know it was the electromagnetic current? Because we assumed a photon was absorbed at a point. And that takes us back again to this idea that currents were the doorway to new quantum field theory for the strong interactions. And it was, in fact, the electromagnetic currents or electroweak currents. So historically, the assumption that photon couples the hadron by a point-like current operator, of course, this is built into the standard model. And what a triumph the standard model is in this and other ways. So the cross section, so here, these are things which just real quick. All the pieces of the cross section are here. The differential cross sections, the square of the amplitude A, that's the whole amplitude we had before. Here's our momentum conservation. P plus K should be Px plus K prime. We sum over X in the deep and elastic inclusive cross section. Let's average over spins, and that's where this, actually, maybe it should have been another 2 here. No, we have 2 squared because we average over the spins in the initial state, right? Just the electron, and we sum over the electrons, scattered electron spin. So we don't have a half of that. Okay, these are just normalization factors for the phase space. So in A squared, so here's the part where people said, okay, how can we analyze this a little bit more carefully for the this matrix element about which we at this point know nothing, except that there is such a matrix element. So we separate into a leptonic part, which we know, and okay, this is just sum over spins of the square of the Dirac functions at lowest order in QED. And after doing that, we get this kind of familiar form, where what have we neglected in this? Is this the whole thing for an electron? What's missing? Something's missing. The electron has a brother, you might say. I'm just saying in this formula. What if we were really doing this exactly? What would we have here? We've neglected something. The electrons. No. Well, no. There's a 1 over q squared for the photon, but that we'll have. Right. This is just this trace for these. This is completely well defined. So the electron U of lambda, Dirac taught us, how to calculate these. Well, not personally, but close. Okay, but there's just something missing in the formula. There's another parameter in quantum electrodynamics, which is the electron's pet fish, lunch. Ah, come on. A, B, C, D. Okay, it begins with M. I think I heard mass, right? We've neglected the electron's mass. All right. Yeah. Right. Okay. Of course, we'll come back to that massless electron, okay, because it's kind of neat, because it is very much relevant to QCD, because for many processes, we can neglect the mass of the quarks, and that's partly what makes the analysis so interesting as we go along. Okay. No, but yeah, well, you always should look at formulas and see what's missing, because there's always something missing. All right. So this, when we take into account also the photon propagator, this leaves us with this hadronic tensor. Okay, I mean, it wasn't like we knew ahead it was going to be a hadronic tensor, but that's what we get when we take our amplitude and we square it. Notice, by the way, there's something neat and quantum mechanical about this. This whole story about multiply amplitudes and then square. The fact that the current here has an index nu, the current here has an index mu. That index is different in general in the amplitude and the complex conjugate amplitude. And that's the sign of quantum mechanics. You're not just squaring an amplitude, you're getting interference terms when you square the complete amplitude, okay? And the L mu nu also, you get different indices, and that's what you put together with these to get a scalar, and hence the cross section. And the cross section is L mu nu, W mu nu. Well, W mu nu, it's nice. On the other hand, it has 16 components, which is kind of complicated, but the known properties of the strong interactions constrain it. And here, you can have, in fact, an entire semester in which we reduce this spin averaged cross section to 2 functions out of 16. But basically, the example, the main one, the most important one for us is current conservation. that d mu j mu should equal 0. Okay, and that follows from the electron by you can prove it with just using the Dirac equation. For the proton, we have to assume that the electromagnetic current to which the photon couples is conserved. And if you think about it, it's like both totally obvious, because if it weren't, then charge wouldn't be conserved. On the other hand, it's totally not obvious because you don't know what the theory is at this point. Okay, so, but anyway, supposing that d mu j mu equals 0, that becomes in momentum space q mu. This is the momentum of the photon. Exchange contracted with w mu nu should equal 0, and the other way too, q nu with w mu nu. So the other things, the strong interactions were known to be parity conserving, and people had very, very good experiments to show that by the late 1960s. And time reversal, that takes a little bit more, going back to the textbooks and checking it out. But at the end of the day, there are only two tensors which are available that you can make out of P and Q and the metric tensor that satisfy all the requirements of current conservation, parity, and time reversal. And so you get W mu nu, so you have W1 and W2. And so these are often given in terms of dimensionless structure functions. F1 is W1, F2 is P dot Q W2. There's nothing profound about this. It's just that the okay, why W1 and W2 have different dimensions. You can see that because W1 multiplies a dimensionless quantity. Now W mu nu is dimensionless, and that's sort of fun to prove. Right? You have to remember what the dimensions of state are, right? But you can do that because the contraction of two momentum states has to be a delta function in the momenta. And so working that out, you find that W mu nu defined the way we did it is dimensionless. So W1 has to be dimensionless because this is dimensionless, the tensors. But here you have dimensions mass squared, because it's P mu and P nu. So W2 has dimensions 1 over mass squared, and then the dimensionless F2 is just that. So, okay, if there were no other mass scales in the momentum, the F's could only depend on Q through X, because if you have a dimensionless quantity and you want to say, well, how does it depend on some dimensionful quantity? There has to be another dimensionful quantity to make it dimensionless. So that, by the way, I mean, this little sentence here is really the way that, in some sense, the way that Bjorkane came to what's known as Bjorkane scaling, which we'll see in a moment if I ever get us there. Okay, so what happened, right? So we know this happened. I said it happened. And there's this really cool thing called the Callan-Gross relation, which really was developed just at the time these experiments were being done, or just slightly after. So from the basic parton model formula, you have this sigma EH. Here's our hadronic part on the left, the thing we measure. Here's the thing we calculate, the elastic scattering cross-section times the parton distributions. So here's a trick, which is what we're all doing all the time. We say, oh, suppose we replace our hadron by a parton. All right, in this case, we can do it too. And then here's our d sigma elastic scattering, EF dq k prime. Well, it has the same form. It's L mu nu, W mu nu, but it's the W mu nu for an electron on the parton of flavor F. Okay, that's the meaning of the F here. All right, so then we move right along and let the charge of F be EF, and then you can calculate this W mu nu. And this is what you get when you calculate it. You get delta functions. It should be dimensionless, is it? It is. No. And here's the thing that becomes the W. It's 1 over C P dot Q. So I said it's an exercise. Well, it's not. But it's sort of fun to do. I find these sorts of exercises like super frustrating, because I sit down and think it's going to be so simple. I'll just do this before lunch, and dinner coming around. whatever, but it's easy actually. And so here's the W mu nu. And so you can decide, you can see here, this is our F1 or our W1 here, and this is our W2. And notice that W1 and W2 are obviously very, very strongly connected to each other. In fact, so then now that you have this W for your electron parton, you can find, you just substitute in, it says 1. I'm hoping this thing, yes, it has an equation number. I took out the equation numbers in everything except for this one. Okay, so here's equation 1. Once we have this in terms of structure functions, we can find out what the phi's are, okay, for our partons, when H is itself a parton. And when we do this, we get that F1 and F2 are connected. You can do this here. We did this, and what we did this for was a parton, which is a Dirac fermion. Okay, but we could also do it for a scalar quark instead of a Dirac fermion quark. And what we find is that one of these F's vanishes and the other one isn't 0. Okay, I forget. It's embarrassing, but I can't remember which F vanishes. So therefore, the result we get for these F's, which is just, it means just we're calculating the cross section. We're finding it's different for spin 1/2 and spin 0. So all of a sudden, out of this essentially trivial formalism, you get an experimental verification of the spin of the partons. And the spin in the data turns out to be spin 1/2 because F1 and F2 are related in this way. Okay, so that's neat. And so this Callan-Gross relation, which is verified, shows the compatibility of the quark and parton models, and its success identifies partons as spin 1/2. So it really is quarks. Sorry, Feynman. In addition, parton model structure functions are independent of Q squared, which is a prediction of that. And that's a property called scaling. With massive partons, there's just no other massive scale. So the F's have to be Q independent. And that was the observation we made a few minutes ago. And so this approximate properties of the kinematic region explored by Slack. So this really worked from the late 1960s to the early 1970s. And then by then, QCD was in place. You had predictions for how scaling would be violated, and those really work. So corrections to these are so-called QCD evolution, which will come about. So now we have reached essentially the end of the first lecture. And there are a set of quark distributions. There's some slides, I think it's about 4 or 5 slides, which are really, again, review, but they're less review. Oh, yes, we have a question. Whoa, I'm sorry, I couldn't hear. Oh, you mean individually? Not so much. They correspond really to different dependence on the angle. Like one of them would be sine squared and the other would involve cosine squared. So it'd be that kind of difference in terms of, and I'm sure we could, give a difference in terms of probably in terms of how the parton couples to different spin components of the photon. So in the next couple of slides, which we're not going to go through, we're going to give how people thought about parton distributions at the very beginning. So these are simplifying assumptions like isospin symmetry, symmetric C, you can get quarks and antiquarks. I mean, you have to think, so neat that the idea that these simple pictures, if there were quarks, wouldn't there also be antiquarks? And then you say, well, wouldn't there? But why are there antiquarks? Because we're talking about a quantum field theory, even though at that point you wouldn't know what it was, but it has to produce quark pairs. So you have then hints of this full quantum theoretic underlying symmetry and so forth. So there's isospin symmetric C, then no heavy quarks. Actually, not all the heavy quarks were known. It wasn't until 1974 that the charm. So you only really had U, D, and S. So they were adequate to early experiments. No longer. You've seen, already heard lectures about what we really do today. But in any case, you get formulas that look like this in the parton model, how your different Fs for electron scattering through neutral currents. So it really should say photon N there. And then you have for W plus and W minus in terms of different antiquarks. And it's sort of fun to do that if you have time. And then you get things that are called sum rules. Now, so let me just say what sum rules are. The number of U quarks in a proton would be given as the integral from 0 to 1 dx, phi of U in P. So that's the notation here for the parton distribution for the U quark in P. And if you do U in P minus U bar of P, because the pairs don't count towards the quark model, so that part, the C part cancels, that should be 2. So there should be 2 U quarks. And, you know, it works. And then there's just examples of the Adler sum rule and the so-called Gross-Llewellyn-Smith sum rule in the parton model. Another one, which is really neat, is the Bjorkane sum rule, but that involves spin. So what else have we got here? So there are things I've called appendices, quarks in the standard model, which I know you've had applications of these. Here I tried to, you know, put a few of these things together, right, and left-handed quarks. Then how they couple in the standard model, weak SU2. The fact that the mass eigenstates of the quarks are not the same as the interaction eigenstates of the quarks. And in the recent decades, we've learned that's also true for neutrinos, but it's for the quarks that are relevant here in QCD discussions. And the so-called CKM matrix, which measures how rotated the mass eigenstates of the quarks are compared to their interaction eigenstates. Actually, it's just amazing. In fact, when you think about it, they're very close. The CKM matrix is very close to a diagonal matrix. So why why? Yeah, why? Okay. And some extent, the LHC was built to answer questions like this, which it hasn't quite done yet. Weak vector bosons, how they couple. Yeah, this is sort of neat. I mean, this is like there's a symmetry of weak isospin, you know, but it's one of these symmetries that is a broken symmetry. And the reason, so you could think of the breaking as saying there's a difference between U quarks and D quarks. So the electromagnetic interactions are like obviously tell us these two are different. They have different charges. They also have different weak charges. And the transition between the North Pole and the South Pole is like the emission of a W plus if you go from the North Pole to the South Pole. And you know it's the North Pole because of electromagnetic interactions, which is the sort of North Star. Well, okay. I just like that picture. So here's the standard model interactions. And okay, I'm not going to go through these. These are symmetry violations, just parity, CP. We're not going to be dwelling on these in these QCD-centered lectures. And then here's a little bit something that somewhat a different way of looking at the F1 and F2 structure functions and photon polarizations. So these are the possible polarizations of the photon. Say we pick a frame where it has energy nu, where nu is P dot Q over MP, okay? So that would be the energy transfer in the rest frame, okay? So this is like, it's similar to Y, except that it's missing a K naught to make it Y. So those would just be the energy of the photon. And then you go to a frame where it only has 3 momentums. Say this is 0, 1, 2, 3. The 3 momentum should be larger than the energy because it's space-like, so it's square root of Q squared plus nu squared. And then it would have right-handed, left-handed, and longitudinal polarization. So in case you're interested, you could have a look there. And so our alternative expansion of W mu nu could be done in terms of the photon polarizations and structure functions associated with them. And so it says exercise 4, but one can go through the lowest order calculation and find out that the left and right polarizations give F1. So that's actually, it was a perfect question. So thank you again. It's F1 tells us how the hadron is interacting with physically polarized photons, and the longitudinally polarized photon, which is only possible because it's off shell. The photon is off shell, is given by F2 over 2x minus F1. And you notice this is just the Callan-Gross relation divided by 2x. So in the Callan-Gross relation, the longitudinal photon, the photon whose polarization is along the direction of its 3 momentum, okay, is actually given, this longitudinal F would vanish if the Callan-Gross relation is satisfied exactly, which it is in the parton model, but which there are corrections from QCD. And so this is one of the beautiful tests of QCD. And then the rest becomes F1. So F1 is in this picture. Of course, the fact that F1 is F2 over 2x approximately means that both F1 and F2 are given by the coupling to the physical polarizations. So yeah, okay, F longitudinal vanishes in the parton model. And yeah, here's just to give a sense of where all this fits in, right, to the larger scheme, especially people are interested in the electron ion collider or experiments at Jefferson Lab, something like that now in electron hadron interactions. If you, or once you allow Z exchange or W exchange, you know you have to allow for parity non-conservation. And so you get a new structure function, W3. Okay, and these W's, all of them depend upon whether it's a photon, the W, or the Z, but they're depending on that only because of the different linear combinations of parton distributions that the different bosons couple to. Okay, so but fundamentally, in terms of parton distributions, they all have the same information up to linear combinations. And okay, F1 and F2 are determined the same way. F3 also, if you look at this one, it multiplies a tensor, which is epsilon mu nu lambda sigma, p lambda q sigma. So this is a characteristic parity object you would get when you have parity non-conservation. And just again, once we have spin in there, and as well as the possibility of W and Z exchange, we get all 3 Fs, but then we get here with spin, we get 2 new structure functions. The thing that used to be just F3 becomes a G1 and a G2. It turns out that this quantity in front of G2 vanishes as you go to large momentum transfer. So it's actually, G2 is something that's really hard to measure. And that's, people are doing that now at Jefferson Lab, I think. G1 is much easier to measure and is a subject of intense measurement interest since the mid-1990s, actually. In the mid-1990s, it was found that, whoops, I hope I haven't done something to the microphone here. Oh my gosh, I'm like going way over. Okay, this I think is the last slide here. This is of intense interest because it turned out that these delta Fs, which are a measure of how the protons, of the quark contributions to the proton spin, they turned out to be smaller than people expected. And it went by the name of the spin crisis. And then, you know, it was kind of cool. People are trying to make too much of it, I suppose, but that's what we do as physicists, because we see a deviation from our expectations, and we always assume that we're right to begin with. So we think this must be something profound. And of course it is. It shows that there are other sources of gluons of spin than just simply the helicities of the quarks. And these are really coming into, in certain ranges of X, precision measurement now. And the electron ion collider is designed to probe this kind of information in new kinematic regions, as well as new features of proton structure. And parton modeling, let's just talk about this afternoon, okay?